Picture this. Somewhere beyond Neptune's orbit, hurtling through the darkness at impossible speed, an object appears. Not from our solar system, from somewhere else. Scientists train their instruments toward it. What they see defies everything they know about comets. It's emitting something, a refined metal compound, the kind that doesn't form in nature, the kind that only exists in human factories. Its trajectory is wrong. Its chemistry is impossible. And what it's doing next shouldn't be happening at all. This is 3I/ATLAS, and it might be the most controversial object ever detected in our cosmic neighborhood. The discovery, July 2025. A hyperbolic trajectory cuts through our solar system. Astronomers mark it immediately as interstellar, a visitor from beyond our stars. They catalogue it as 3I/ATLAS, the third confirmed object from another system to pass through ours. At first, it seems like just another cosmic wanderer. Massive, yes. Unusual in size, but nothing to sound alarms over. Then August arrives, and everything changes. The WMEK Observatory turns its instruments toward ATLAS. Spectroscopic analysis begins. The data streams back to Earth, and in the laboratories where astronomers pore over the readings, silence. 4 grams per second. That's how much nickel Atlas is venting into the void. Pure nickel, streaming from its surface like industrial exhaust. But here's what makes every scientist in the room lean closer to their screens. There's no iron. None. Imagine finding a car with an engine but no wheels. A bird with wings but no body. That's the magnitude of this impossibility. In every comet, every asteroid, every natural object humanity has ever studied, nickel and iron appear together. Always. They're cosmic partners, forged in the same stellar furnaces, traveling through space in lockstep for billions of years. Atlas breaks that rule, completely. But the real shock comes when they identify exactly what ATLAS is emitting. Nickel tetracarbonyl. The impossible compound. On Earth, you'll find nickel tetracarbonyl in exactly one place: industrial facilities. Aerospace manufacturers use it for specialized coatings. Metallurgical plants synthesize it for refining processes. It's a compound born from human engineering, from controlled reactions in pressurized chambers under precise temperature regulation. It does not form in nature, not on Earth, not in asteroids, not in comets forged in the frozen outer reaches of alien star systems. Until now, every telescope that can reach ATLAS turns toward it. Hubble, James Webb, ground-based observatories across the globe. They all see the same thing: an interstellar object bleeding industrial chemistry into space. But Atlas isn't finished revealing its secrets. As astronomers study its movement, they notice something else. Something that violates the basic physics of how comets behave. Atlas has no tail, no sweeping arc of dust and gas trailing behind it like a cosmic banner. Instead, there's a jet, and it's pointing in the wrong direction. Solar wind pushes everything away from the sun. It's not a suggestion, it's fundamental physics. The radiation pressure from our star drives gas and dust outward, creating the iconic tails we associate with comets. Atlas doesn't care. Its jet aims directly toward the sun. Multiple instruments confirm it. This isn't perspective trickery or observational error. The jet is real, and it's moving sunward. Picture that for a moment. A stream of material. Carbon dioxide, water vapor, trace cyanide, and those nickel compounds, all flowing toward the sun, against the cosmic wind that should be pushing them away. Chemical anomalies deepen. The chemical analysis gets stranger. Atlas carries a carbon dioxide to water ratio of 8:1. For context, that's among the highest ever recorded. Most comets show ratios closer to 1:1 or maybe 2:1. Atlas is drowning in CO2, emitting 8 times more of it than water vapor. Then there's the polarization data. When light scatters off Atlas's surface and dust grains, it behaves in a way scientists have never quite seen before. Extreme negative polarization. The dust structure, the grain size, the way material is organized on its surface, all of it suggests something fundamentally different from familiar comets. Every measurement adds another piece to a puzzle that refuses to make sense. In early October, opportunity strikes. The Mars Reconnaissance Orbiter's high-rise camera, one of the most powerful imaging systems ever launched, has a clear shot at Atlas during its flyby. Scientists prepare for the data that could finally reveal the object's surface structure, its jet morphology, the physical reality behind the chemical impossibilities. The images capture. The data begins its journey to Earth. And then, nothing. A US government shutdown delays the release. The scientific community waits. Debates intensify. Hypotheses multiply. But the one piece of evidence that might settle the controversy remains locked away, tantalizing and unreachable. The natural explanation. Most scientists approach Atlas with caution. The data is bizarre, yes. Unprecedented, absolutely. But extraordinary claims demand extraordinary evidence, and there are natural explanations that could account for what we're seeing. Consider the possibility that Atlas formed near a CO2 ice line in its home system, a region where temperature and pressure conditions differ dramatically from anything in our solar system. Perhaps in that alien environment, iron and nickel separated in ways we've never observed. Different temperature gradients, alternative elemental processes, chemistry following rules we haven't encountered because we've only studied objects born in our neighborhood. Over millions of years traveling through interstellar space, ATLAS would have been exposed to cosmic radiation. High-energy particles bombarding its surface, breaking bonds, rearranging molecules. Maybe that radiation selectively altered its composition. Maybe it allowed nickel to outgas freely, while iron remained locked in the object's core, bound in mineral structures we can't detect from here. When Atlas enters our solar system and solar heating begins, perhaps those exotic conditions trigger chemical reactions. Uncommon, yes, but still natural. Reactions that produce nickel tetracarbonyl through pathways we simply haven't discovered yet. Laboratory experiments are underway. Scientists are recreating interstellar conditions, testing whether natural processes can generate the compound under extreme cold, radiation exposure, and then sudden solar heating. It's plausible. It fits within the boundaries of natural science. It requires no extraordinary assumptions. But there's another explanation, one that's harder to dismiss than many would like to admit. The other possibility. Avi Loeb, chair of Harvard's astronomy department, looks at ATLAS and sees something different. A sunward jet. Refined metal emissions. A trajectory that shows characteristics difficult to explain through gravitational interactions alone. Chemistry that mirrors human industrial processes with unsettling precision. He raises a question that makes many of his colleagues uncomfortable. What if this isn't natural at all? The term he uses is technosignature, evidence of technology, of engineering, of deliberate construction. In this framework, the nickel tetracarbonyl isn't a chemical accident. It's exhaust. The sunward jet isn't an anomaly. It's controlled propulsion. The trajectory isn't random. It's navigated. Most scientists resist this interpretation, not because it's impossible. The laws of physics don't forbid artificial objects in interstellar space. They resist because the evidence, while strange, hasn't crossed the threshold that would make such an extraordinary conclusion necessary. Science operates on parsimony. When faced with an unusual observation, the simplest explanation that fits the data is preferred. And right now, exotic natural chemistry is simpler than interstellar technology. But Loeb's point stands. Atlas presents a combination of features that, taken together, are difficult to reconcile with purely natural processes. Each anomaly individually might be explainable, but all of them appearing in a single object? That makes scientists pause. What this means for science. Regardless of which explanation proves correct, ATLAS has already rewritten parts of the textbook. For planetary science, it provides direct evidence that other star systems form planets and comets through processes that can diverge significantly from our own. If nickel without iron is real, if that holds up under peer review, it challenges fundamental assumptions about how metals distribute during planetary formation. Our solar system formed from a specific molecular cloud with specific temperature gradients and elemental abundances. We've built our models on that foundation. ATLAS suggests other systems may follow different rules entirely. Consider the pattern emerging from interstellar visitors. Oumuamua, the first detected, showed non-gravitational acceleration without any visible outgassing, behavior that still lacks a universally accepted explanation. Borisov, the second, looked exactly like a typical comet from our own solar system. Now ATLAS arrives, massive, chemically anomalous, dynamically unconventional. 3 visitors, 3 completely different profiles. Interstellar space isn't populated by one type of object. It's filled with diversity, bodies carrying the unique chemical signatures of their home systems, each one a messenger from worlds we'll never visit. The bigger picture. ATLAS also teaches us something about detection and interpretation. When astronomers first spotted its sunward jet and refined metal emissions, some jumped to conclusions. The data looked artificial. The compound seemed engineered. But this is precisely why science moves carefully. Natural phenomena can produce signals that appear designed at first glance. The universe is creative, capable of generating complexity through blind physical processes that can mimic intention. Future surveys will apply this lesson. The Vera Rubin Observatory, once operational, will increase the detection rate of interstellar objects dramatically. Instead of one every few years, we might see dozens, eventually hundreds. Each one will arrive with its own set of anomalies, its own challenges to existing models. Scientists are developing protocols: rapid multi-wavelength follow-up, spectroscopy within days of detection, polarimetry to characterize surface structure, high-resolution imaging to capture morphology before the object speeds away beyond observation range. ATLAS proves the value of this approach. Every instrument that studied it, Hubble, James Webb, ground telescopes, Mars orbiters, contributed a piece of the puzzle. Only by combining all those perspectives does the full picture emerge. Waiting for answers. The high-rise images still haven't been released. When they finally arrive, they'll provide crucial insight into ATLAS's surface structure and jet behavior. Scientists will study the morphology, the reflectivity, the physical arrangement of material on its surface. Those details could tip the scales toward one explanation or another. Meanwhile, JWST continues tracking ATLAS as it moves away from the Sun. The observatory measures how the nickel emissions change with distance, whether the jet evolves or remains constant, whether new compounds appear as temperature conditions shift. WMEK Observatory maintains its spectroscopic watch. Every data point refines the measurements, narrows the uncertainty, brings clarity to the chemical composition. Peer review continues. Other teams attempt to replicate the findings, to verify that what was detected is real and not instrumental artifact. This is how science progresses. Through careful validation, independent confirmation, rigorous skepticism applied equally to all claims. If the nickel without iron anomaly survives this process, if it holds up under the scrutiny of the global scientific community, it will mark a major expansion of what we know is possible in the universe. Far from Earth, beyond the orbit of Mars, beyond the asteroid belt, ATLAS continues its journey. It came from darkness, passed through our brief moment of observation, and will return to darkness again, traveling for millions of years before it encounters another star system. We had months to study it, a cosmic blink. And in that blink, it challenged every assumption we held about interstellar objects. A comet that emits industrial compounds. A jet that points toward the sun. Chemistry that resembles Earth's factories more than any natural body we've encountered. A ratio of elements that shouldn't exist. Surface properties unlike any known comet. The next observations won't just explain ATLAS. They'll expand the boundaries of what we think is possible in deep space. Because if natural processes can create something this strange, this unexpected, this impossible, what else is out there, moving through the dark between stars, waiting to be discovered? And what will those visitors teach us about the universe we thought we understood? Atlas isn't the last mystery. It's just the first one we noticed.